implement what a computer scientist would recognize as an abstraction hierarchy supporting programming in DNA. So we'll just make this up and see how it goes. Parts are basic biological stuff, and we'll hide the DNA and we'll give it a number and we'll give it some functional information so you could use it without having to know all the biology. And then we'll build devices out of parts. These are just a bunch of numbers. These 4 parts come together to make an inverter or a NOT gate, Boolean logic. This turns out to be a bad design because the input and output signals aren't the same. So we reorganize the black box and we make a common signal carrier inverter and blah, 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 blah. Then you put the inverters together to make a ring oscillator, and we're bootstrapping up an abstraction hierarchy. If that didn't make any sense, you can go to the web and get this comic strip which explains how to implement abstraction for genetic engineering. Okay. So as a result, we now have the beginnings of an abstraction hierarchy. It's incredibly primitive, but practically what it lets you do is somebody gets to become a systems engineer, the other person at the bottom becomes an expert DNA constructor. The person at the top doesn't need to know that DNA is made up of 4 bases, but you still get to engineer a biological system. In doing all of this, we're stealing lessons from all other forms of engineering. So mechanical engineering from the 1860s, where in the US, thank God, we finally got standardization of screw threads, 60-degree angles squared off at the top, so that things snap together and work when you put them together, so long as you don't mess up the English metric stuff. We started a registry of standard biological parts. These are open source genetic objects, parts.mit.edu. There are about 2,000 different parts in the catalog right now. They stink. They're not very well characterized. They haven't been refined to support reliable functional composition, but they will snap together and you can see what happens. Here's our best part. We've got a data sheet, for example. This is a receiver, a genetic receiver. You put this in a cell, and the cell stands ready to respond to a small modified sugar or a signal that comes in from the environment.